Right, so let's look at the previous problem from 15.3. We're going to use the polar coordinates to find the volume of the given solid. Okay, this is the question. Hold on. Use a polar coordinate to find the volume of the given solid. Right. And this is 21, so it's below. It says that below this, below the plane, and 2x plus y plus z equals 1, and above the disk, right? X squared plus y squared less than equal to 1. Right. So step 1, you have to draw the picture, right? So you draw the picture. Here's the axis, this y axis, z axis. Now a disk is on the xy plane. Okay. So make sure the plane is above the disk. Okay. When x squared plus y squared is less than equal 1, and I hope, yeah, otherwise it's not very clear here, right? It's going to be 21. This is a 4, I think. Yeah, it's 4. So that means z equals 4 minus 2x minus y. Okay. So based on the problem, you were told that this plane should be above the disk. Otherwise, how can you say below the disk, right? Now, if it's not, then only portion of that will be above the disk. Okay. So make sure this is above disk. Okay. Now, so this is a let's see. I think the normal vector of this plane is going to be 2, 1, 1. Okay. So normal vector. Let's think about that. Normal vector to this plane is going to be 2, 1, 1. Right? It's clear. So it's point to that direction. Yeah, it's hard to draw it. And when x, y, z equals 0, that's when x, 0, y 0, z is going to be 4. So the plane passing through that point, okay, going this way, it's hard to draw it. It's not horizontal. So let's draw a slightly different way. I think it's going that way. Okay. Yeah. So where does it touch to, in order to make sure this plane is above the disk? Maybe you can look at this intersection point, right? Yeah, if the intersection is away from the disk, I'm pretty sure this plane is above the disk, right? Yeah. So otherwise, it's cut through the disk, then some portion of the plane is below the disk. So if you ask to find the volume of the solid above the disk, then be careful, it's not over the whole disk. So make sure, right? How do you look at the intersection point? The intersection point is when z equals 0, right? So this one is z equals 0. So the equation will be 2x plus y equals 4. Now, when you draw the graph, yeah, when you draw the circle, as a circle has radius 1. Okay, and this line, when x equals 0, y is 4. When y is 0, x equals 2. I think I'm pretty sure this is away from the circle. Okay, it's away from the circle. Yeah, we probably don't need it to let me draw. Yeah, it looks like that. It's 1, 2, 3, 4 going this direction. Okay, so this is a line. I'm pretty sure it's far away from the circle. Yeah. Okay. So we are safe. Now the picture on the plane, the intersection part will be looks like that. Okay. Yeah. So the plane cuts through the cylinder. We're trying to find the volume of the cylinder. So set up the formula first. The disk is denoted by D. Okay. So the volume, how do you solve? The volume is going to be double integral over D. Okay. And the value of the function, and actually Z is going to be 4 minus 2x plus y and dA. Okay. Yeah, this is a graph. Yeah, the graph is Z is going to be, yeah, this is a Z. Z is going to be 4 minus 2x minus y. So the function at every point, the height is going to be determined by the Z value. Right, so this is a volume formula. The double integral of the function is going to be the volume of the solid and the graph of this function. Now, next step, once you set up this, then you have to think about how to get the evaluate this double integral. Now you focus on this two-dimensional picture. Okay, the functions over this disk. Okay. Okay, this is set up. Can you spend half minutes to think about to translate it to a double integral over a rectangle in the r theta coordinate system? Right. Right, so we're going to use, if you already watched the video, or attend my classes, that's what I'm talking about. This is so you're going to find a rectangle. Okay, this is R, this is a theta. Right? So the rectangle, how do you describe this disk, right? It's going to be, x is going to be r cosine theta, y equals r sine theta. So clearly, r is between 1 and 0, theta is between 0 and 2 pi. So you imagine this is a map, okay? From this rectangle in the r theta plane. So this rectangle is mapped to the disk, almost cover 1-to-1. Okay, there's some small areas overlap, but it's okay. It could be neglected. So this is a map from this disk. So it's kind of substitution, similar to, we are going to use a two-dimensional substitution to simplify this integral. Okay, and this domain is called a D. Okay, and the area element is called dA bar. Okay, so this double integral is become the integral over D bar. Okay, and for x, and x should be replaced by r cosine theta. Y should be replaced with r sine theta. But there is a part shows up coming from the called the derivative of this map, okay, which is just r. Okay, we already derived that formula. So this is a part coming from the derivative of this map, okay, from the rectangle over to the disk. Okay, don't miss that part. And this part is just replace x by r cosine theta, y by r sine theta. This is a still original function. Okay, this is a function, but now in the new variables. Okay, but these are coming from the derivative of this map. In one-dimensional case, it's easy to see that if you have, yeah. So you want to understand this formula, right? In one dimension, it's easy to understand. Here's a and b, and you have an integral of this function, right? But now you find the so-called substitution. This will be a bar and b bar, and I'm going to use a map x equals h over t. So this t is from here, right? So then the integral of ab can be changed to integral a bar to b bar, and here f, where x is replaced by h of t, then don't forget there's a derivative of h. So this is the dx. Okay. So in hard dimensional case, there's something similar to this is very similar to that part, right? Then there was a similar to this part, goes up here. So our special transformation, yeah, gives you the derivative of this map in here. So this is coming from the derivative of this map in some sense. Okay, we call it Jacobi of the map. Okay, so we already did as a computation, and for the special transformation, you will get R. Okay. Now the next part is to evaluate this double integral. So the rectangle, the region is rectangle right now, so it doesn't matter which one is first. You can evaluate the integral from 0 to 1. Then you put the dr outside, and from 0 to 2 pi, then 4 minus 2r cosine theta plus r sine theta. Okay, then d theta. Okay. And then there's r here. Don't forget the r, right? We have r. We did here multiply by the r. This is yeah. So r is outside. So I'm going to put r here, r here, square and square. Okay. So now evaluate the integral with respect to theta. I think the integral cosine theta is going to be 0. Integral of sine theta will be 0. Okay, over the integral from 0 to 2pi. So only this first term plays rules. It's 4r times 2 pi and dr. Okay, you don't need to find the antiderivative because integral of sine cosine theta over the whole the integral from 0 to 2 pi because it changed sign. So that's why I cancel out. Okay, so now it's going to be 8 pi r. Okay, I think this is the answer. Yes. Yeah. The integral of a cosine theta is going to be 0. Okay. Integral cosine theta. And integral of sine theta also is going to be 0. Okay. Yeah, let's go back to look at another explanation is, think about this. This is a double integral, right? The double integral is going to be, yeah, think about this double integral, okay? Just think about this double integral, and here 4 minus 2x minus y, right? dA. So d is a circle, right? And this is a d, okay? X-axis. Now you can separate it. Okay, it's going to be 4 dA minus 2 d double into dA and minus y dA. Okay, and I claim without using polar coordinates, I can get an answer here. This is so special. First of all, the first term is constant, so A times area of D. Okay, right? Yeah, take a constant out. The integral of constant 1 over D gives the area times 4. The second part must be 0. You know why? They're all 0. So the answer is 4, and the area of these pi are square. R square is just 1, so it's just 4 pi. Wait a minute. Where's my R from? No, there's yeah. Sorry, yeah, don't laugh. Yeah, there was a mistake. Yeah, the R is not constant. So we are going to evaluate 4R because this is a 4R dr. Okay, so they're much better, right? So the antiderivative is 2R squared, and there, so it's 2. Where's no. We have I have a 4 pi there. Sorry. No. Come on. So this is a constant 4, right? Then have a 2 pi. Okay, 2 pi and the dr. Okay, so actually it's 4 pi r. Okay, then antiderivative is 4 pi r squared from 0 to 1. So that's been 4 pi. Okay, it's clear? Yeah. R is a variable again. So r squared, 4 pi r squared is the antiderivative. Okay, then evaluate the two endpoints. That should be 4 pi. No wonder. Okay, so now that's why I get 4 pi here, right? So the unit disk, the area is pi. So 4 times pi. So get same answer. Okay, I did not know that. So why the integral of x is going to be 0 over the disk? Okay, because over the disk, okay, just focus on this. Why is this is you don't need to waste time to why is this going to be 0? Okay, the reason is look at the x value over this disk, and here x value is negative, here x value is positive, right? So that cannot cancel out. It's by the symmetry. Okay, the right hand side, the left hand side, they are the same size, same domain almost, and the x value positive, x value negative, so that should be canceled out. Okay, so that's the reason it's going to be 0. So I don't need to use the polar coordinates to prove this is 0. Okay, this integral is 0, and similarly, the integral of y is also 0. So that's the reason only the first term plays through here for this double integral. Okay, so look at that. It's quite simple. I don't need to use any polar coordinate. I still can quickly get answer to 4 pi. Okay. Yeah, it's 4 pi. Okay. All right, so today's section is 15.4. It's applications of double integrals. We are only going to focus on the first part, the moment and the sentence of math. Okay, so section 15.4. Yeah, we're not going to talk about all the topics. So I will only assign like 5, 6 problems for this section. Okay. So if you have the center of mass, yeah, if you have a region D, okay, it's in 2-dimensional plane, okay, and you have a density function. Rho is going to be the density function. Okay, we want to know where is the center of mass. Somewhere here, depends on density function. Okay, we want to find the center of mass. So the idea is use a calculus idea. You can derive this formula. You can project the whole region onto Yeah, let me draw the coordinate system in that way. Okay. So you can project the whole region onto X, onto this X-axis. Okay. So then, if you know all the mass collapse to projected to this axis, so your density function will be different. Your density, they all accumulate along this line. So think about the density function. So then you will get density function for x, right? Which is going to be the integral of the density function over the whole line. Okay. Yeah. Then then you're trying to find the center. So it's become one-dimensional case. The center, okay, x bar is the first coordinate of the center of the mass in the three-dimensional space. Then x will be the center of this new, it's one-dimensional, right? So x will be the center of this piece with density function x bar. So if you know that, then we know how to derive that formula. So x bar is going to be the integral of the total mass, right? And the numerator is going to be x. Okay. Then you go back to the double integral. Okay, you can show that this is going to be, you know, if you replace low bar by this integral, you will get the double integral. Okay, so below xy dy dx, right? Think about it. And here will be double integral x, so xy dy dx. Okay, so in other words, this is supposed to be the double integral of this density function, which gives the total mass, and this will be the double integral of x. Okay, so that's the way we. This is how do we get the formula for the center mass, and similarly, y bar is going to be the double integral of this. And the only difference here is just change x to y. Okay. That's it. Now, there's a new terminology for this. This part, the numerator of this, called the momentum about the x-axis, not about the y-axis. Okay, and the other one, yeah, this is called and this is called the momentum about the y-axis. No, forget the name. We're more interested in to find the center of mass. Okay, using those two formulas. So nothing's new here. This is just the definition of center mass, and or we can call it formula. Then just evaluate the double integrals. Okay. So let's take a look at some problems. Pretty complicated. It involves three integrals you have to evaluate. Okay. So let's find the yeah, let's do problem number 2. Number 4, yeah. Right. So we have a domain D, and it's described by the following. So actually, it's a rectangle, right? But the density function is not constant. It's going to be 1 plus x squared plus y squared, right? And so we find the mass and the center of that. All right, how to do this problem? Well, by the definition, okay. First of all, you draw the picture. So this is a rectangle, and here's A and here's B, okay? But the density function is positive function. And so mass M is going to be the double integral of the density function over that D, okay? So we have to evaluate this double integral. Well, this is a rectangle, okay? Rectangle region. So okay, we can quickly evaluate that using the iterative integrals. Doesn't matter which one is first. You can let x to be outside, then dy should be inside. Right. All right, so let's find the antiderivative of this function with respect to y variable. Here's y plus x squared y plus 1/3 y cubed. Then you plug b for y. Right. Then you get a function of x as a constant. And yeah, this will be the antiderivative. Right. And then you plug a for x. You should get an expression a and b are in equal position, okay? Because this is a function of 1 plus x squared plus y squared, x and y in equal position too. So here's going to be b plus 1/3 b cubed a, and here's 1/3 a cubed b, okay? When you write down the details, you will get ab, okay, 1/3 ab cubed plus a cubed b, right? That's pretty nice. Yeah. So this is the mass of the rectangle with the density function, given density function. To find the center, we have to evaluate this double integral x. Okay, this is called the moment of about y axis. Okay. So this is going to be dA. So the only difference here is just multiply rho by x. So I'm going to, yeah, it's x1 plus x squared plus y squared and dA, right? So I think I'm going to get rid of x first when I iterate the integral, and this time I'm changing the order. So give me x plus x cubed and xy squared dx and dy, okay? So the antiderivative of that function will be, this will be x, actually x plus, this should be 1 plus y squared, half of x squared, 1/3 x cubed. Okay, then I plug a for x. I get 1/2 of a squared plus 1/3 a cubed. Finally, yeah, how do you get the antiderivative? The constant should be taken out, and this will be y squared, so a squared over 6 y cubed, and plus 1/3 a cubed and the y, and evaluate at 2 endpoints. Okay, so we're almost done. Okay, so I'm inheriting to find the x bar because I already got the x, got the numerator, right? So x bar is the ratio of those two. So let's find out what is my x. I forgot the answer here already. It's ab 1/3 ab cubed, right? So ab plus 1/3 ab cubed plus a cubed b. And here, oh, I think I can take a square out. I can take a b, also take a b out. So a square b, it can be out. Okay, 1/2 plus b square of 6 and plus a over 3. Yes. So denominate, you can take a ab out. Yeah. So let's rewrite this. ab out. It's going to be 1 plus 1/3 b squared and plus a squared. So after you simplify, ab square, a square b over ab, just a left. Then 1/2 plus b square over 6 plus a over 3, and yeah, that's pretty. That's good. Now, do I need to waste time to find the y coordinate? I think y bar. I think I just needed to interchange a and b, because the integral is similar. Okay, so all I have, the y bar is the double integral of y rho xy dA. I think I already know the answer here, because all I needed to do is interchange a and b. I'm pretty sure, yes, the denominator still is the same. So the numerator will be a square over 6 and b over 3. I'm pretty sure. Okay, so I'm not going to waste time to do the calculation. The reason is the function rule, x and y in the equal position too. Okay, and so whenever the x becomes y, and the a change, a and b can be exchanged. So a becomes b, b becomes a. Then you get this answer. Okay. So I'm not going to repeat the same computation for this particular problem. But we are going to look at slight different one. That's number 10, because the domain will be different, right? So D is enclosed by the curve, okay, y equals 0, and y equals cosine x. Okay, what is x? X is restricted between negative pi over 2 and positive pi over 2. Okay, the density function is going to be y. Okay, let's just find the find the mass. Okay. Now let's try and find this first. If we have more time, we can find the x bar, okay, or y bar. This is just double integral. Okay, so m is going to be the double integral d and the rho function. Okay, so this is just double integral. So write down the formula first for that. All right, so now then you have to draw the graph for the domain D. D is a cosine x, cosine, something like that, okay? All right, negative power 2, positive power 2. I think this is the region we are talking about. Yes. All right, so this is how do I evaluate this double integral? Well, use the iterative integrals, right? So the idea, let me repeat again. So you use a rectangle, okay? This is called R, right? My original domain called D, right? And then the density function could be, inside is still equal to Y, inside D, but outside is going to be 0, okay? So I'm going to let tilde xy to be y if xy is in D. Otherwise, it is going to be 0. Outside D. Okay. So then this is going to be the integral of R rho tilde. Okay. Then you can apply the iterative integrals because rectangle as the domain is going to be a rectangular region. Okay. The rectangle region here is on top one is 1, right? So y is between 0 and 1, x is between negative power 2 and positive power 2. So now it's up to you, but I think that we should use x for the x outside. And this will be dy and dx. Okay? So this will be from 0 to 1 rho tilde. But this rho tilde is going to be 0 if it's outside the domain D. When it's outside domain D, when the y value is larger than the cosine x. So cosine x. So it's going to be integral from 0 to cosine x. Then it becomes rho. Okay? Yeah. This rho is going to be y if the y variable is smaller than cosine x. Look at the picture here, right? It's smaller than cosine x. Yeah, this curve is y equals cosine x. So if y is greater than cosine x for the fixed x, then it's become 0. So that's the reason you just needed to focus on this interval from 0 to cosine x. Right? Then the entire derivative is y squared. Finally, you get half of cosine square x dx. Okay, to evaluate this integral, you have to use the double integral formula or the half integral formula. Okay, so you have to rewrite this function in the following form: 1 half cosine 2x. Right? Yeah, cosine square. I have to change it to cosine 2x. Okay, in order to evaluate. Okay, so the entire derivative is a quarter, right? And x1 becomes x cosine 2x will be sine 2x over 2. Okay, this is the entire derivative of cosine 2x. Okay, evaluate at the two endpoints. I think the second part will be 0 because cosine pi is 0, sine pi is 0, sine negative pi is 0. So the only will make difference is x evaluate at the two endpoints. That's going to be pi. Okay, so this will be just pi over 4. Okay. All right, in this particular for this particular problem, you should put dx outside when you use the iterative integrals, because this is then it's easy to determine the y value. Now, if you don't want to do that, this is double integral, right? This is y dA. If you want to put dy outside, what happens? Okay, it's still from 0 to 1, no problem. And this will be from negative pi over 2 to positive pi 2 to that. The only trouble is you have to determine the interval for rho tilde. Look at this. Right? This is a y equals cosine x. Now for the fixed y, you have to determine the 2x value. Because right now you are in R, right? This is a, yeah. Yeah, that's right. So in the middle, there is okay. So you have to, the rho tilde is going to be 0 outside this domain D, okay? Now for the fixed f, for the fixed y, the x value of those 2 points is going to be, you have to find the what? You can find the, you have to find the inverse one, right? Yeah, it's not easy to figure out. So for the x, yeah. So you got 2 x values. This one I called arc cosine y. Arc cosine y only gives you one value, okay? And then this will be negative arc cosine y, okay? So in order to replace y rho tilde by original density function, then you have to change it to this. And here's y and dx and dy. Okay, then it becomes more complicated. Then so dx is so no it's twice of arc cosine y and dy. Then the question is, how can I evaluate this integral? Yeah, you can still evaluate this integral. You have to use a integration by parts. Okay, you can do that. You differentiate cosine arc cosine y, but still works. But it's more complicated. Okay, integration by parts. Okay, what is the derivative of arc cosine y? I think it's negative 1 over 1 minus 1 over square of 1 minus y squared. So this is a I'm not going to continue because this is it's not the best way to solve the problem. Yeah, if you use the integration by parts, and you will see that, yeah, just look at the antiderivative. Just trying to find the antiderivative of this first, right? And this will be dv, that's du, right? And v is going to be y squared. So v is going to be y squared. So uv minus v du, this is where you find the antiderivative. And then y squared arc cosine y, and this y squared. When you differentiate arc cosine, you get negative. Okay, then you end up with this. Okay. Then you have to find another way to solve the problem. Okay. So this is not the best way to do. So you be careful when you choose iterate in the order of iterate integrals. Okay. Sometimes you end up with a more complicated integral. So the order is very important. All right. Let's look at problem number 8. Okay. So D is bounded by y equals x plus 2 and y equals x squared. The density function is kx squared. Right, cool. So step 1, you have to draw the, what are we going to find out? Find the mass. Okay, I'm not going to find the center of mass. It's too much work. I find the mass. Okay. Well, draw the domain first. X equals y equals x squared like that. Y equals x plus 2, it goes like that. All right. And you have to determine 2 intersection points. Right? 2 intersection point is x squared equals x plus 2, x squared minus x minus 2 equals 0, x minus 2, x plus 1 equals 0. Okay? My answer is x equals 2, x equals -1. So this is a -1. This is 1 and -1 when x equals 2, y is 4. Okay? So this is a domain, D. We're going to evaluate the double integral of the density function over this D. Okay. But so to skip some steps, I don't want to draw the domain, a rectangular region R. I just how do we get the iterate integrals? I'm going to use vertical lines to cut through this region. Okay, x is from -1 to +2. So for any x, okay, so this will be the integral. It's dx. Okay, x is from -1 to +2. So the density, what is density? Density function is kx squared. But I have to determine the domain for the fixed x, the domain as the interval for y variable. For interval, the y variable is from here to here. As this is a piece, right? So y is the lower y value is going to be x squared. The upper bound for the y variable is going to be x plus 2 because this is on the line. Okay. You can skip them some steps. Actually, this is coming from the, you change it to the integral of a rectangular region, and then you have to change the density function. So this r, what is r here? R is going to be this rectangle. Right, this is r. Right, this is a d. If you want to use r to understand, then it's okay. Otherwise, you can do it directly. Just choose a point x on the x-axis. Okay, then for an arbitrary fixed x, then you draw a vertical line, and you can see the line segment going through the region, and only over that region you can evaluate the integral. So you have to find out the lower bound for x, for y, and the upper bound for the y variable. So now, kx squared kx squared is constant with respect to y variable, so it's kx squared, then only the difference. Okay, of those two endpoints. Right, now you can multiply, you have to multiply this out. It's going to be k, it's still put outside, and that will be x cubed plus 2x squared minus x to the 4th power. Okay, let's find the antiderivative. 1/4, and here 2/3, and the 1/5. Right? So I shouldn't put the integral symbol here because I already have an antiderivative. So be careful not to do the computation. Be careful about this. 2. Right, minus negative 1. Plug a negative for that, right? Just 1. And this negative is become negative 1/3. And this becomes positive 1/3. Right? Okay. So let's simplify it. 2 to the 4th power. 16 minus 115 over 4. And then I have the addition here. Okay. So 16 plus 2 is 18. Yeah, this is a negative. And this will be add them together. Okay, 2 to the 5th power, 32. 32 plus 1, 33. I think that's it. I don't think we needed to add them, combine them into one fraction. If this is a problem on the test, all right, you stop here, move on to the next problem first. Don't try to waste time. When you have a time, go back to, because there's more important problems later. Otherwise, you're going to run out of time to do the computation. Or you can even stop here. Then say, I know how to do it. Just need more time, careful, right? So you move on to the next problem. And until you finish all of them, some problems, maybe you're stuck there, you have to figure out how to do it, right? Because you get more points on the ideas, less and less points on the computation. Okay? It's not easy to get 100 points, 100%, because you are a human being. It's easy to make an error, just like what I did, the one of the examples. I saw this constant. I do not pay attention. This is an integral with respect to r. Until I try a different way to solve the problems and say, oops, why the answer is different? And I go back, okay? So honestly, I never got 100% on all my calculus tests when I was a student, okay? I usually get to 95, 98. I'm doing good, but it's harder to get 100%. This is not because you don't know the material. It's easy to make mistakes, okay? But do not make too many mistakes. That's fine. So the last week have test was the last test. Nobody get 100%, okay? Nobody get 100%. Some students make small mistakes. All right, we don't have much time left, all right, for the quiz. So let's take the quiz. I also bring the older quizzes, exams here, so don't forget, take them back, okay, when you turn in the quiz.